Okay, so if you just stop for a second and listen, really listen,
Mm.
you can probably hear a whole range of sounds. Maybe it's the hum of your computer, maybe a car outside.
And the difference between that quiet hum and, say, a loud siren is just, it's enormous. If you tried to measure it with a normal ruler, the numbers would be in the trillions.
Right. And that massive difference isn't just in your head, it's physics. It's all about energy.
Exactly. And that's what we're getting into today, the science of volume. We're going to look at the physical laws that control how much power a sound carries and why your ears are such amazing but also fragile receivers.
So let's start with the basics. Sound itself isn't really a thing, is it? It's a form of energy.
It's a wave of energy, yeah. It happens when something vibrates, and that vibration pushes and pulls the air molecules around it, creating these little changes in pressure that travel outwards.
And volume is just how we perceive the intensity of that energy.
That's it. A stronger vibration at the start means more energy in the wave, and what we hear is a louder noise. So our goal here is to break down how that energy works, how we can control it, and, what happens when it gets to be too much.
Okay, so let's get right to the core physical property that makes a sound loud or quiet, and that is amplitude.
Amplitude is the key. It's really just a measure of how far the wave moves from its resting position when it vibrates.
So the size of the wave.
The size of the wave, exactly. If you think about the energy you put in, a stronger vibration creates a bigger displacement,
Sure.
and that equals a greater amplitude.
The drum analogy is perfect for this. If you tap a drum really gently, the skin barely moves.
Right, maybe just a millimeter or two.
That creates a small pressure wave, low amplitude, and you get a soft sound.
But if you hit it hard, you're creating a huge displacement in that drum skin. That huge movement means a high amplitude wave, and we hear a much, much louder noise.
It's a direct translation then. The amount of energy you put in directly creates the height of the wave.
You can also picture it like the ocean. A calm sea just has these little ripples, right? Low amplitude.
Yeah.
But during a big storm, you get these massive, powerful waves. Same water, just a totally different amount of energy, which results in a very different amplitude.
And that's so important because it shows that two sounds can have the exact same pitch.
Meaning they vibrate at the same rate.
But if one of those waves is much taller, if it has a higher amplitude, it's going to sound way louder.
Right. So because that difference between the little ripple and the huge storm wave is so massive, we can't really measure it on a simple linear scale.
You'd run out of numbers.
You'd run out of numbers fast. So we need a special unit that can handle the entire range of human hearing.
And that's the decibel, the dB.
The decibel, yes. And what makes it so useful and so powerful is that the scale it's logarithmic, not linear.
Okay, so why can't we just use a linear scale? I mean, why not just make the unit smaller if the range is so big?
Well, because the difference in shear intensity is astronomical. The loudest sound we can handle has about 1 trillion times more energy than the quietest sound we can possibly hear.
1 trillion.
1 trillion. If you tried to measure that in a straight line, the numbers would just be meaningless.
Okay, so the logarithmic scale kind of squashes that huge range down.
It condenses it. And here's the part that's really important to grasp. Because it's logarithmic, every time you go up by 10 decibels, you're not just adding a little more sound.
What are you doing?
You're multiplying the physical power of the sound wave by 10.
Whoa. Okay, so say a normal conversation is, what, 60 decibels?
How about that?
And a loud truck goes by at 80 decibels. That's not just a little bit louder, it's...
It's 100 times more powerful. 10 times 10. That's why high-volume sounds can feel so overwhelming so quickly. The power increases exponentially.
So if 0 dB is the quietest sound we can hear, going from 90 dB, like a lawnmower, to 100 dB, like a subway train, that's 10 times more stress on your eardrum.
Instantly. And having a standard like the decibel is just, it's vital. It lets engineers, doctors, everyone communicate clearly about noise levels and safety limits all over the world.
Speaking of the eardrum, let's talk about the biological side. How does our ear actually interpret all this amplitude? How does it turn a pressure wave into something our brain understands?
It's just a beautiful piece of mechanical engineering.
Mm-hmm.
First, your outer ear acts like a funnel. It catches those pressure waves and directs them down the ear canal.
Until they hit the eardrum.
Until they hit the eardrum, which is this thin, taut membrane. And that's where the energy changes form, from a wave in the air to a physical movement.
That vibration.
A vibration. The eardrum starts vibrating, perfectly matching the frequency and the amplitude of the original sound.
And those vibrations get passed along to 3 tiny bones, right? The smallest in the body.
The hammer, anvil, and stirrup. They act like a set of levers. amplifying the force of the vibration and passing it along to the inner ear.
The mechanical genius there is it's incredible. To take a complex pressure wave and turn it into this focused vibration.
And that vibration finally reaches the cochlea, which is in the inner ear. It's filled with fluid, and it's lined with thousands of these tiny microscopic sensors. They're called hair cells.
And these are the final step.
They are the final conversion point. They take that mechanical movement in the fluid, and they turn it into electrical nerve impulses that the brain can finally process as sound.
So the connection to volume is really simple then. The bigger the amplitude of the original sound wave, the harder those little hair cells are forced to move.
And the stronger the electrical signal they send to the brain. The brain interprets that stronger signal as louder.
But there's a little bit of a catch, right? Our ears aren't equally sensitive to all pitches.
Not at all. We're much more sensitive to mid-range frequencies, which is, where the human voice is. So you could have two sounds that have the exact same decibel level, same physical energy.
But one might sound louder to us just because of its pitch.
Exactly, which is a perfect reason to officially separate volume from pitch. We've been talking around them, but they are totally independent.
Okay, so let's lock this down. Volume is determined by
Amplitude, the height or the energy of the wave.
And pitch is determined by
Frequency, which is just how fast the wave vibrates, how many waves pass by in 1 second.
Right. Like on a guitar, you can pluck one string, the pitch stays the same because it's the same string vibrating at the same frequency.
But you can pluck it really softly or you can really slam it hard.
Same pitch, completely different amplitude, completely different volume.
And the reverse is true. You could play a super high note on a piccolo and a super low note on a tuba, and they would both be at the exact same soft volume. Different frequencies, but the same amplitude.
Okay, so we know how sound starts and how we hear it. What happens when that sound energy leaves the source and goes out into the real world? Why does it fade away so fast?
That is the effect of distance, and it is nature's most powerful volume control. As that sound energy travels, it spreads out in all directions, like an expanding sphere.
So the energy gets distributed over a bigger and bigger area.
Right, and it's governed by something called the inverse square law. It sounds complicated, but it's pretty simple.
Break it down for us.
If you double your distance from a sound source, say you move from 5 feet away from a speaker to 10 feet away, the sound intensity doesn't get cut in half.
No.
It drops to 1/4 of its original level. It decays really, really aggressively. That's why a highway that's deafening when you're next to it is just a faint hum a mile away.
And it's not just distance. The environment itself plays a huge role.
Oh, absolutely. The air itself absorbs some energy, and then you have obstacles, which gets us into how different materials handle sound.
Hard surfaces like concrete or glass, they reflect sound.
They're highly reflective, yeah. They bounce the sound waves right back at you, which creates echoes and makes a room feel louder.
That's why an empty room sounds so loud and echoey.
Exactly. But soft materials like carpets or heavy curtains or that special foam you see in studios, they're designed to absorb sound energy.
How do they do that?
They basically trap the wave. And the tiny bit of kinetic energy from the vibration gets converted into an even tinier amount of heat. Think about a movie theater. The walls are covered in fabric to soak up all those reflections and control the sound.
But what if we need to do the opposite? What if we need to make a sound louder to fight against distance and absorption?
Well, then you need amplification.
Yeah.
Which is just the process of adding more energy to the wave.
And today, that's almost always electronic.
Right. A microphone captures the original weak sound wave and turns it into a tiny electrical signal.
And then the amplifier takes over.
The amplifier boosts that small signal using voltage to make it exponentially stronger. And that much stronger electrical signal gets sent to the speaker.
And the speaker uses magnets to push the air with way more force than the original source ever could.
Creating a new, much higher amplitude wave that can travel much farther. It's how we fill a concert hall, or even just how the tiny speaker in your phone works.
Let's pivot to maybe the most important part of all of this, safety. We talked about how amazing the ear is, but those little parts are also incredibly fragile.
This is the critical takeaway. Loud sounds are physically dangerous because of the energy they carry. Any sound that's consistently over 85 decibels.
Which is about the level of heavy city traffic.
Right. Over time, that can permanently damage the delicate hair cells in your inner ear.
And here's the thing, they don't grow back.
They do not grow back. Once they are damaged or killed by too much vibration, that hearing loss is permanent.
So if you're in a loud environment, a concert, a factory, even a construction site, for any real length of time, you have to protect your ears.
It's not optional. Earplugs, noise-canceling headphones, you have to reduce the amplitude that's actually hitting your eardrum.
And taking breaks helps too.
A huge amount. Stepping away into a quiet space for even just 10 or 15 minutes lets those structures in your ear recover from the stress.
It's pretty amazing how much control we have over volume in the digital world, though. How does my phone make something louder or quieter without a physical knob?
When sound is recorded digitally, the amplitude of the wave is just stored as a series of numbers.
So it's just data.
It's just data. And to change the volume, the computer just does math on that data.
It's that simple.
It's that simple. If it multiplies all the numbers by 0.5, the wave gets smaller and the sound is quieter. If it multiplies them by 2, the wave gets bigger and the sound is louder.
That mathematical control is what allows for so much precision. And for safety features, like setting maximum volume limits.
Exactly, linking that digital control right back to physical safety.
Finally, let's look at how this all plays out in nature. Animals don't have electronic amplifiers, but some of the loudest sounds on Earth are natural.
Absolutely. Volume is a strategic tool for survival. A lion's roar isn't just noise. It's a high-amplitude warning that carries for miles, marking its territory.
And on the flip side, a lot of smaller animals use very quiet, low-amplitude sounds to communicate so they don't attract predators.
Silence becomes a survival tool. And then you have animals that use the physics of their environment to their advantage. Whales are the ultimate example.
They can communicate across hundreds of miles of ocean. How?
Because water is so much denser than air, when a whale produces one of its massive, high-amplitude sounds, that energy travels much more efficiently. The medium itself doesn't absorb the energy as quickly as air does,
So the wave maintains its power over these incredible distances.
allowing them to communicate across an entire ocean basin.
So understanding volume, amplitude, and that logarithmic decibel scale is really fundamental to understanding how energy moves through our world and how to protect our own incredibly complex ears.
And as our technology gets better, our ability to manipulate volume, to cancel noise, to focus sound, it's only going to get more sophisticated. It makes you wonder, how will future engineers use this precise control over amplitude to reshape the sound of our world? For communication, but also for our health.
Good luck with your studies.